So in IP course and IP course and design hierarchies, we're gonna talk about those two topics, but also a lot of questions in between. But you have to put me into the window again. To then go later for the rest of the design workflow. So we come today to the separate design blocks, focus on VHDL, but similar principles also exist in Verilog. So we're going to focus on VHDL and on the overall systematics of building a VHDL design in a quite flexible way. The lecture goals going to be what VHDL design blocks exist. So you might have heard of those before again, but I do not know how much you went into this in the last course. I wanted to give this as a good foundation and a toolage for the next assignment, so you're aware of those. Then we have how is a typical design built. So I'm going to introduce a design hierarchy, what are IP cores, and what is a block design. So these are abstraction layers to work with. We have in this VHDL design blocks, we can group this into, it's not a standardization whatever of groups, but I grouped into 5 parts, which is basically the entities, architectures, and configurations. That's essentially your big block. It's a module, you could call it. Each entity has an architecture and, or at least one architecture, multiple architectures, which is then changed or selected through configurations. You have, if you want to, that's the minimum you need to have. And then everything else below depends on the design for each of the entities. So in an entity, you can have processes. I'm going to introduce all of them in a second in a bit more detail. Components and instantiation. So components are actually other entities used in an entity or in an architecture to build blocks up. And you have functions and procedures, which feed into packages and libraries. You can also define functions and procedures in architectures, but generally you use them to make a library, so a package and then multiple package to make into a library. So you can then use it over multiple designs. So if you work in a company, you might have your own design library consisting of various things. Entities and architectures. Entities define interface to the module, so the wrapper, if you want to call it like this. They can have input, output, in-out, and buffers. But as mentioned in the past, in-outs and buffers are less relevant. That's why they're grayed out. They will make your things more difficult, and they're going to be only used in very niche scenarios. And I've still not encountered any design where I would absolutely need it. And the other part is generic parameters, which essentially allow you to give configurations into your entity. So how wide is my bus, how many data blocks, what clock speed do I have. These kind of things can be set through generics, and that's usually numbers and natural numbers, integers, whatever you need. And they are essentially like the interface, but also the blueprint and the black box. So when you are in other design formats, which you're going to come later to, you're also going to see, that's what you're going to see. That's the interfaces and whatever you have listed until you open it up and you go into it. The architecture describes what happens in the entity. So how the entity operates internally and also how it may connect to other entities. So there's a behavioral part, so how does it work, and then a structural part, how does it connect to the others. You can technically split the entities into, and you can split architectures into those two types. They can be separated, but they can also be a mix of both. So you can have some structural parts, so some connections defined and then have still a behavior. But very often people use it use a structural part to make an overview, have all the different components in there, and then they do only everything in each of the subcomponents. It's a bit cleaner, but it's a design choice or a design style choice. Both of it works. And gonna show how these things connect in later a bit, I think. Configuration is, last time I had a question if you can have multiple architectures per entity because you give them a name. When you can name them, you can obviously give them more. The question was, how do you select it? Because it's such a niche thing, I never myself actually used it because that's actually mostly used for switching, implementation, testing, optimizations. So you actually can make a simple architecture which does not fulfill all the needs, but will drastically decrease your simulation time. Because you have to, the simulation, every signal you need to simulate takes extra time technically, so if you make it simpler, you will save a lot of simulation time, so you can change here the different architecture types to make it much faster. For example, all the error correction, whatever you might not need in a certain simulation, and then you leave it out. And you change your configuration for that. Yes, so this configuration selects all the between the architectures. You can also in your workflow automatically let them select according to a specification you've given in other places. But again, this is something which I generally would advise to not use in the beginning because it might be confusing at some point. Or which architecture did I use now? And you do not need it. It just can help you a bit. Actually, can I? No. Fine. The next part is processes. Also, it's not going to be a very long topic today, I think. The processes are, well, the upper parts are very simple. They are just typing down. You got to be very careful that you connect things correctly. There's a real big hazard of connecting things incorrectly, or like one port to another, and then you have a mess of components and all these kind of things, and they send the signal to the wrong entity. Did it go to sleep? Oh, okay, interesting. And then the big part is where the processes, and that's actually where the big coding happens, and that's where you implement your performance, in my opinion, and all the kind of things which actually do something, unless you make like only a signal routing where you connect architectures to each other. It's essentially, processes is like, you can imagine it like almost a bit like a CPU code, although depending how you write it, it will do everything at the same time still. Everything which does in the process will happen iteratively at the same time. So it's a sequential block within the architecture, so you write one thing after another. They are technically done, but if you have a trigger, and we're going to come to this, I hope, sensitivity list. When you have a trigger like a clock, then everything will happen, and will only be checked again at the next clock. So it does not happen at the same time, but also it happens at the same time, relevant for your design or your workflow. It describes a complex behavior and triggered by a sensitivity list. This is, and these things are overall, this exists similar in Verilog as well. This basically triggers what designs you will look for, or which designs will activate your process. So just to give, do we have? Yes. To give you a small example. So I have a processor, I can give it a name XX, you do not have to give it a name. And then you can do root process. Then you have here a bracket. And you might have seen this before in VHDL code. And usually, there are two of these in there. There's reset and clock. And now I can go in here, right, if clock rising, whatever, I will just write it roughly, rising, then I will go in here, or else, I don't know if I have a reset. But this is a asynchronous reset. So this means the reset will trigger at any time, right? What I actually want in a fully sync, so this is, I have not talked about this, we're going to come to this, I think, in place enroutment of like asynchronous and so on, but I'm going to touch on it very briefly now, that you understand the principle. This will, because it's in the sensitivity list, it will trigger both when both of the signals are being changed, which may be that I just had a clock pulse, and then actually the reset signal changes, and then it will go into it again. So that's one thing which I have to be careful about. And second of all, it's asynchronous. So I will have to consider in my FPGA routing design that I want to have this as fast as possible at any time available. And then you come into weird signal changes in between where you do not do this at different things. So what you actually want to do is, you do not want to have here, this can be a design choice that you make it like this, but generally you would make if clock, and then you make if reset, and then you do your clock, or else, oops, else, and the rest. So basically you only trigger your reset when your clock signal is there as well, because usually your reset, honestly, your reset signal is going to be longer than your clock signal. So that's what the sensitivity list does. The thing is, technically it should always only trigger according to the reset, but if you have then in certain scenarios it can. So always take care of that you have both, that you have it synchronized to a clock and that you do not have it up here. Where it becomes useful on the other hand is when you have a finite state machine. Let's call it so you have an unclocked process, which is technically asynchronous. It's not anymore that often used, but also just to understand, you have state 1, state 2, state 3, whatever, right? And then you have a case when I am in case state 1, and when I get the signal and so on. And I have case state 2, and then I have case state 3. When I forget one of them here, I will never get into the state because it is not in my sensitivity list. So it is something to consider. Also, I noticed that when you have a state where actually the transition is triggered through, for example, ready signal from a bus interface, right? I'm waiting for the signal, I want to switch to the next state to process the data. Then it becomes annoying because you have to put all of them up there, and that might annoy you when you forget one of the signals and you do not understand why it does not trigger.
Is it ASM or PSM?
This?
Yes.
It's a FSM. It's a finite state machine. Sorry.
Oh, close enough.
Yeah. I just try to visualize it a bit. The text does not matter that much because you can just name them as you want.
Oh, it's just a name, XX.
Yeah, this is just an XX, and that's also just a name. We might have a code later where you can see it briefly. It's also in the other codes. So that's the sensitivity list. This is going to be quite important for in synchronous designs that the clock is on there, and in asynchronous designs that you are sure that you have all of your triggering signals in there. Otherwise, you will lose or will have a weird bug where you do just not see why does it not go into there. And this, of course, can then get quite complex because you do everything in there. This is often, when there's a simple design, these things are used and state machines are used in processes. But when it gets more complex, actually people like to implement a small processor for the control because it gets really, really complex from the state machine point of view. The purpose is to have clock operations, state machines, and the other part is conditional logic. So I want to, if I do this, I want to do this. And key elements as set is one time the sensitivity list, and the other part is signals, and we'll also grayed out again variables, because variables will just confuse you in the beginning when you work with it. So basically, you work with the signals, you assign them, you compare them, you do whatever you want with your signals, and you get triggered, and you trigger your process according to the sensitivity list. Yes, I think that's roughly it. Components and instantiations. The components are basically enable a reusable design that can be declared and used in another design. Sorry, I have a block design and I create a component out of that block, and then I can use that in my current architecture, for example. And it enables hierarchical design and design hierarchy and interconnections of multiple components. So it allows me to have in one architecture multiple components, or in one entity multiple components, which I then can interconnect to different things, almost like a data router, if you want so. The instantiation will basically instantiate a component, which will basically make as many components as you want. So you can have one component, which you define, and then you can create 10 of them. And I will have one of the slides where you can see this a bit. And then you can basically have components within another architecture. Basically, this will allow you to pull in one design into another, and then have embed one design into another one. And then you can build from a lower level up to a higher one, which is quite nice. And this, of course, then I do not have to write every time my UART or my router or my FIFO or everything. I can just always use the same thing. it's efficient and easy modification. Of course, you got to be careful when you want to change one, it will change in all the places. But that's how libraries and everything is. Yes, functions and procedures. We'll have an end of that, actually, a short question. A function is a self-contained block, as same as a procedure. It takes one or multiple inputs. That's the same for both. Maybe I could have put them next to each other. But they are the same, but they differentiate drastically in how they are written and what they actually then can do. The function always returns one, I should have written here one output. So it's not one signal, but it is a signal vector or something like it's one kind of parameter.
Isn't there some kind of end block? It doesn't exist.
Not for the function. So I mean, of course, you could combine multiple signals, but also it can only read input values and then combine them and give a result. So you have a very limited options in that scope, and will be executed sequentially. If you want to do what you just asked for at the end, I would just use a procedure, because that will can give none or multiple back. The function is just a very, very small block if you want to make your code more better overview. I've actually mostly used procedures, functions quite rarely because of the limited functionality. And the difference is function will give a return. So it's like literally like when you call a function, and in other languages as well. The procedure you assign to an output. So it's almost like, when you have two ways how to give values back. You can also write it into another global variable compared to programming languages, and this will be available outside. Not that it's the same thing, but for you to understand. And then, of course, here this one can, obviously, because it needs to give outputs, it also allows to change the signals and the variables you have given in. And this is mostly used here, actually, for bigger steps, so that you do not have to write 1,000 lines into your architecture. Then you make a package with all the different procedures or functions, and this will allow, for example, complex operations. You can initialize all the values which you may need. So, for example, a reset, you can just wrap into a procedure, and then you have it outside of your main code block, and the code block will be small, and you will just call it init, and then it's somewhere else. And then you have setting control signals, similar, and algorithms, especially algorithms. We often use it like for checksums and those kind of things. They will be outside, otherwise you have AND, XOR, and yada, yada, yada in a line, and like it just blows up the code, and you're like, what is this? You always want to have it quite clean and simple, and especially in VHDL, otherwise you will not find your signals where everything happens. And of course, when you do an init, you will never forget to initialize a value somewhere, so that's quite useful. So we have a function and a procedure. The question is, so basically we make here and return A and B, so it just combines the signal values. On the right side you have an input ABC, and you get an output value. And then the result will be whatever you do and these kind of things. Which of the two responses do you think fits to which one? I will make it simple for you. So this one gives a return value. So it is like a normal function code, it will return. And the other one writes into the result variable, so it just writes into the output. And you actually write just the function call. It's something which you have to get used to when you use it, but in the end it is hopefully not too difficult. So basically you write here into a parameter which will be later accessible, which you have overall in your design already. Questions on that? Okay. And of course, that's just to wrap this up. Oh my God, I'm going way too fast. Oh no. We can maybe show some in code examples just for the workflow, because it's very theoretical and dry. We have here packages and libraries. As said in the very beginning, contains declaration of multiple design files, data types, constants. So actually in VHDL you can create your own data types, which is quite useful. So you can actually make multiple dimensional arrays and those kind of things in this. because VHDL itself does not have these things. There's at least something there. So it's a bit similar, I think, in C you can also do that. And so you can make your own data type structs or whatever. So it is kind of useful. And constants. So you do not have, so you have actually could make a package or a library, sorry, a package in this case, which has everything defined, all the constants, and then you just have to go in there and change all the files instead of doing this in your code. And then, of course, as I said, you have functions, but it can also include entire components. And of course, this is quite useful when you over the years develop a code library in your company or wherever you do this in your projects, and then you can just reuse this and organize and structure your code. Also very useful for highly optimized code, because I can spend a lot of time optimizing it, then I can reuse it. I can make different versions of this for logic utilization, for timing optimization, so I can play around there a lot. And then, of course, I guess the obvious is that a library consists of multiple packages, and that would be the way how you facilitate the packages overall, and then you can just load them into your project. And of course, then you find open source libraries, vendor libraries. You find libraries from companies which you can buy in. So basically, everything which we just discussed about, you can pull in libraries. Not everything though, but gonna come. I think not everything. Not everything. Just basically ready to, written code and formats. Now we come to the core part of the lecture, as I've shown you the different blocks. From the last assignment, you hopefully maybe remember something like this. I've not had this diagram there, but we had a design hierarchy which has a test bench, a UART simple which connects to both, and then a RX and a TX. Which looks, for those who have not graphically remember this, maybe in the Vivado design, it looks like the UART loop and then two on the same level, RX and TX, and then here with the test bench and the simulation with the test bench above. Just for the reference. Exactly. What did I want to? Yes. Oh, no, I don't have. No, I can't. Oh. We're going to figure something out after this. So we're going to show the technical stuff a bit later. It's going to be a bit easier. Yes, exactly. That's the obvious what I meant. Because we don't need my face on that, the camera. And if you blow this a bit up with different architectures and so on, it gets quite confusing and very big. I'm going to go through this bit by bit. So on top you have the test bench entity. In this case, I've not made this blown this up also into all the different parts, because it has an architecture, has a process, has components, because it kind of includes everything below. So this just for now. You always in your design have like a top entity. That's the one thing which is on top of everything. In a normal scenario, unless you develop an IP core, or even in that, depending how I phrase it now, it's the thing which interfaces with the rest. And the top entity in IP core will just interface with the rest of the FPGA design. If it's in your FPGA or ASIC design in the end, then it will be the thing which connects to your outside pins. So it's actually the physical interface. So it's my reset, my clock, whatever UART or whatever ports I have on here, they will go here into the top entity. And the test bench tries to stimulate those on the outside. And now we come here to just go a bit down here on the left side here. We have the design which we already had. And on the right side, I just illustrate a bit what you, for example, could do. You have basically a structure it's one of the architectures which we have created. That's what you already have. I could although write a second architecture in the same file. With the only difference being though, that I can have here UART RX1 and UART TX1 as processing components. And the process in here, there's also mixed design in this case. I have here just the connection between the two is like the process. And then I have, and it's going to be very hard to see on the picture, you're going to see it better on the video, not so important. You have here architecture behavioral, which does define the TX and the RX behavior, so receiver and the command behavior. Oops. So, and then we have down here the processes. So the architecture is a behavioral in this case, not a structural. And in this case, the behavioral architecture has only one process each. I could also make more, this will come later, but this can spread out into a lot of different things, right? Just to illustrate what a modular design can do, when I have second architecture, I can change my configuration, and I can have two RX ports which feed into one TX port, and that's just purely by changing my modular approach, how many components I instantiated. If it's 2 RX or 5 or 10 or 100, doesn't really matter. I can just use the same things over and over. The only thing which may change is here the process. Depending how I've written that, if I write it very well, it will scale, right? In some whatever way. In the assignment case, it's just for one signal. Of course, I could also just duplicate the process. I could make it here another architecture, a component which has a process, and it will just have multiple of those. And I configure that in here. But that really depends on how you structure your design. And this is just basically this is your design hierarchy. You almost always have something like this, unless you have a very, very simple design like where you do not even interconnect anything. Because here's the top level. Here's the level where you define that in your top level. And that's where you interconnect every other subcomponent. Much less is difficult to have a reasonable example, but this will go also. You can have in here an architecture which defines more components of like FIFO and whatsoever, and then you go down into various ways and into a very deep design. It's also a bit of a design choice. How wide do I want to have my design, right? And how many layers do I put? Because I can easily just also have said, oh, I wrap this as one transceiver here. Then I have a transceiver and I have a UART RxDX, but it depends on how modular I want to have my design. In this case, it would be, for example, constraining. I would need to have even number of RX and receivers and transmitters. If I would make a transceiver. Maybe I do not want to have that. Maybe just from some entities I just want to have a receiving signal, or to some I just want to log it out into a SD card and I will never read from it. Whatever these kind of things are, that's what I can scale and adapt here. So it's a design choice where you have to think from the beginning, and this is something which is underestimated when you start your design. That you look really into the different design blocks. What do I use where? What may I need? Where can I split it up? Where can I reuse? This will save you a lot of time. Otherwise, you write a huge architecture and you realize, oh, I can split it up, and then you have to rewrite it. And especially as VHDL writing is quite slow, and simulating in the process of that is, well, let's put it this way. The time you can save here by thinking beforehand about how you set up your design is much, much higher, the time efficiency, than in other programming languages where you can just try it out and you copy it and you put it somewhere else. And just because of the simulation effort and everything. And also something more complex to simulate will take longer to simulate. Also to verify and those kind of things, of course. Like the smaller your entity, the much, much easier it is to simulate and verify it. Oops. Is that understood, clear?
Maybe later an example.
Yes. I will try to go through it with the last assignment. We'll also come in the seminar briefly, but just for the completeness of that lecture. Now we come basically to IP cores, which basically can be an entire design hierarchy in itself. And that IP core is a pre-designed, well-verified module or block of logic. And I'm going to also come to different types of IP cores. We will mostly work, I think, with like soft IP cores. We'll see if we have anything else. And basically, can be anything. What is IP core? It's very similar to a library, but essentially the IP core is something which, I mean, it's technically intellectual property, of course, but I do not like that name very much because it can just be what you have done internally, and it's kind of both used. It can be a module that's very often called an IP core because an IP core is nothing else than a module, just that you have bought from somewhere else or used it from somewhere. So it's used interchangeably, so don't be confused by the name itself. And but it can be anything from an adder to memory controller to actually full-on processors or anything. We'll also show that in a bit. And there will be some stuff also in the seminar. The pros, I mean, of course, wherever you can get something from outside, it's going to reduce your development time, assuming it works, but that's the standard. It also increases reliability. It definitely can improve your performance. depending even on what kind of IP core you use, if this is soft or hard IP core, we're going to come to that, and simplify complex functionality. So you do not have to think anymore about every algorithm, you do not have to implement your own processor if you need one. There's always going to be an IP core for complex functionalities. Like, for example, you definitely, if you're writing a FIFO yourself, or you're writing a processor yourself, or you're writing Ethernet ports or something like this yourself, then you kind of are maybe doing too much unless you have a very specific need for that. So you can really get so much from the outside, and then you just connect them, or you do your very custom things. Of course, here are some personal cons in here. They can, especially as we have like IP cores which are not open source or something, we will have an encryption and a licensing, which can be annoying. And also with the licensing, there come two parts to it, especially with the encryption. So the encryption is limited inside. If it's encrypted, I will not see anything in there, which can also be for hard IP cores or things. So that's mostly for soft IP cores. And then we have an ability to change things because of a license, and I have an assurance it will work. If I change something, that insurance that it will work is gone, right? So that's kind of maybe constraining, depending how you want to use it. And in many of the IP core types, you actually can't even IP core types. Soft IP cores, it's just a lot of text, so you have the definitions together. Basically, there's three types. Well, with the last one is a mix of it, so technically you have two and anything in between. You have on a soft IP core is basically HDL level, so I have the description level, or as a netlist, so you have basically the design, and you could change and you can access it. It may be encrypted though, so someone might have written an encryption over it to sell that to you. And hard IP cores are actually already pre-configured, pre-routed blocks, so they are already ready to go into your design. They do not change. They are specific also for the device you have right now. And this, of course, comes automatically with benefits and disadvantages of both sides. The soft IP core is, of course, wonderfully flexible. You can customize it, you can change it, you can adapt it. Especially if it's written in HDL code, you can just go in there and change things. However, consider that it's a verified core in many cases. You do not want to change too much. Otherwise, you have to test everything again. Examples are mostly like controllers. Controllers very, like literally, also I think when you write a bus interface yourself, then you also have done something wrong because they exist kind of everywhere, all over open source projects and so on. I'm not talking here about peripherals. They also exist everywhere, but I'm talking about internal interfaces. Will be a separate lecture. We have custom logic optimizable, so I can literally just put it in there, do my own optimizations on it. But again, that will cost me time, right? So it's highly flexible and modified for my design, but on the other hand, I do not get, at least not in the beginning, the ideal performance out of it, because I would need to find the parameters, the settings for my specific device, so that it has the ideal synthesis in place and rootment and the timing and all these kind of things. And thus, it leads to a longer design and optimization times. Just because I have more flexibility means I have more options. More options mean taking more time to figure out the ideal option. And also maybe sometimes people do customize place and route, so they literally move by manually the things around to make it ideal on the chip because the routing algorithm didn't do it as not good enough. If you have a soft IP core and you sell that and you give it away, this will be lost, right? If you make a hard IP where it's pre-configured, you can export this place and route, and you can sell that, and then no one can change it, but also they will get your ideal product. So you will ideally get much less complaints about, we don't meet the performance, but because there's nothing to be changed on the performance. And that's, of course, where we go to very, very high performance and low power consumption applications, which are really optimized to the dead end, where you go towards designs of like, exactly here, I was just about to say it, PCIe, Ethernet, like really the ideal case of memory interfaces where it goes to gigahertz, and every kind of timing difference matters a lot. Obviously, the pro is here, optimized design, ready to use, also with minimal integration efforts, so it's kind of nice. I buy it, I use it. I cannot change anything, so the only thing which I have as integration effort is making it work with the rest. But that I also have with the other parts. That's kind of very minimal, but of course, I cannot change anything. It's whatever you want to pick. Of course, then there's in between where you can configure them, and I will show you in the block design, you can load it in, and then you can configure out of the options, which they of hard cores, you can change some parameters, or they might have configurations. Exactly. And of course, then here's a balance between all of them and processor. Very often, when you get into very big blocks, like processors, you might want to have one core, you might have a different memory type, you might have different interfaces, you might have different whatever cache size, because on the FPGA depending, then you will have something in between where the rough architecture is like hardcore, but additional things or like additional cores or any optimizations you can maybe customize. Yes.
Question from the previous slides.
Yes.
We have the soft IP cores and firm IP cores, both can be a netlist. What's the difference if they are both a netlist?
The firm IP cores, yeah? You mean?
Firm IP cores and soft IP cores, both mentioned as netlists.
Yes.
Differently locked somehow, or?
I mean, the firm IP core is like an in-between thing, right? So depending how much where on the spectrum between soft and hard IP core it is, if it's very configurable, it will be very close to a soft IP core. Also, not every soft IP core you actually can change on a low level. So that's a kind of a flowing, I would see as a spectrum where you have on the extreme sides, you can change everything, on the other side nothing, and then you have a firm and it's like in between. I would mostly go by those, actually, to be honest, and that just the firm is something to be aware of, that it can be anything in between. I can also, and I will change it and upload it as anything in between cores. But you see already a netlist is an intermediate representation, which is often hard to read. And then, of course, when you have a soft core with an intermediate representation, you will have to have a tool which will be able to regenerate these kind of things. Especially also often used when you could get soft IP cores from a HLS, high-level synthesis or so. Then it might be directly delivered as a netlist. So you change it on a higher level, which then will go down. Design with IP cores. I mean, it's a general design flow, just for general understanding. Important, I mean, the most important part is selection, selecting your IP core. And this is a choice. Often you do not have a choice because the library, the scope is not that big. But if you have a choice, you should really look into it, because sometimes it will either not work at all when you make the wrong choice, because, right? Like, I mean, let's put it this way. A 10 gigabit Ethernet IP core might just not work on a simple FPGA. Because of resource overhead of processor clock, which the FPGA doesn't have, or whatever. So you want to look into what does my IP core actually require. Modern tools, of course, when I go into Vivado and I want to use a certain IP core, it either will not even show up, or will tell me you can't use this IP core with this device. But still, you might not want to use over-designed IP cores, because they will just have a huge overhead. And those kind of things. Also, of course, overhead-wise, very important always, we talked about, like when I go to HLS or block design and those kind of things, the higher my abstraction level is, the less customized to my specific need it will be. So I might have a huge overhead which will take half of my FPGA, but actually could have reduced it to a quarter or whatever, right? Because I do not need this functionality, this, and that is still in there and I will never use it. So the choice of your IP core and what it will do, or those kind of things, are very important. Often FPGA vendors provide IP core catalogs in the tools included, and that will give you usually the processors, memory types, bus interfaces, those kind of things by default. And it's often directly in the tool, so you can just literally load up the IP core integrator. They, however, will also often allow you to load your own IP core library. So if you have a company IP core library, you can load it in there and you will use it at this, as the vendor of IP cores, which is, of course, kind of nice. The other part is regarding the overhead is of course parameterization. That's like the other part where you really need to, it allows to customize, again, depending on which kind of IP core you have, bus width, operating frequency. If I go, for example, for AI neural network accelerator, if I have a very small accelerator, I might not need 64, 128-bit bandwidth to send my data in there, right? Because the accelerator is that slow that it will not be able to use this bandwidth, so you will just use a lot of logic, which will be wasted. So design analysis might be useful there, same with operating frequency. So these go together. And also, of course, sometimes actually IP cores with the Vitis AI IP, deep learning processing unit, for example, one of the IP cores, you can make multiple of those. So if you collect 3, then you have 3 times as many resources. But again, if you do not have the bus interface or the data bandwidth in other places, this is not going to be useful. I've seen this in my studies and evaluations that you have like a DDR3 memory, and you chuck all the DPUs on there with 3 or 4, but you can't even load the data out of your DDR because, and then you're like, nice, good that I've configured it nicely to all the maximum spec. It's overall the design, understanding your design and making the right choices. Otherwise, you will just use resources for nothing, or you could have gotten much more performance on the other hand, of course. Exactly, for design requirements, resource constraints. So if I have also not enough logic, you want to reduce that as all these kind of things. Then this is often done automatically, I have to say. Depends where you get it from, especially if you use vendor IP cores. You will click through a UI, or you have written a script which does it, and that will basically start, I will this setting, this bandwidth, this clock frequency, that many cores, and then it will run everything automatically and load out of their encrypted library or whatever, compressed library, and load it into your design and integrate that. Super nice, super useful. And then we will have an HDL file, which of course on top level will specify your parameters and your interfaces, like entity. And then in many cases, you're not going to see the inside because they're compressed, encrypted, especially vendor-wise. If they have something very powerful, the vendor has put I don't know how much money on that, right? So they will not make it openly available. And of course, because now the block there, but now it's just hanging around there on my FPGA. My synthesis tool will immediately throw it out again because it's not connected to anything. I will need to connect it to other components in the design through block design or HDL file. Depends on which approach I prefer. And exactly, and then we come to the normal design flow, I would almost say. Now you just write the rest of your code. Like, what else do I have? Sometimes you might not even need for using Vitis AI, so the CUDA competitor from AMD Xilinx on FPGA. I do not have to touch HDL. I will click button, will load things in, run autoconnect. I will also show that in later, and I will create the entire design, and I'm done. Assuming I did the right configurations. There can be bugs in there. Let's careful to be reliable on this, but it's getting with every year, these kind of tools get a lot better because they want you to use the products more, so they make those things much, much easier. But of course, in every other kind of instance where there's not that much money and not the wide use so much in there, if you have any kind of from FIFO to algorithms or whatever, you will have to, of course, then give the data in, and those kind of things you have to manually do. Also, on older devices and older tools, they do not support necessarily these things, the automatic connection, so you have to write your HDL wrapper on top of that and connect everything to each other. Exactly, so you also have to do on-chip communication to get the data in. There's usually use standard communication interfaces. We're going to have a lecture on that, but I had to start either with interfaces or IP cores. Today we have IP cores, and I think next time we might even have, later we have interfaces. And then you just follow the rest of the workflow. You simulate your design, you check that it works as it's supposed to. Actually, honestly, if you have something like Vitis AI, you might not even simulate it. Because it's so huge, this IP core, that it will just take so long to simulate, and it's quite complex. But if you have a smaller IP core like a FIFO, you want to see that you actually correctly load the data in and out. And synthesis and implementation, just the rest of the workflow. And basically you can do here optimizations, different routing algorithms, and those kind of things. Questions to IP cores? Okay. So this is really in there. This is also, you do not have to do like an end product developer. You can also be saying, oh, I have this idea, I want to code this IP core, and you can sell it. And if it's something which people really want, they give you a lot of money for it. That's how it is. Of course, ideally, you would show them, this has worked on a breadboard, on this board, and so on and so on. But what you have to see is like really, this is just one functionality. And you can sell them by functionality. Especially, there's a company like which does like space processors. They started by developing their own space-graded VHDL-based space processor, radiation hard. And at some point, people liked the cores that much. I mean, they sold them that they actually put them into an ASIC and sell them now as chips, and that is what they base on. And now they're one of the most used radiation space-graded processing cores which exist. Also, of course, you can always just for the fun of it write a RISC-V IP core and do your own new processor, and play around with that. So this is also, of course, very useful for testing out different design architectures before you would make an actual chip design. Where you put into an ASIC which processor, how many cores do I need? I can put on an FPGA, I can play a bit around, and if I buy in the IP cores, it's going to be quite nice. Exactly, we're coming to the end already, from the slides at least. We have block design. This is basically, I would say, a quite modern tool. I do not know since when it exists. It exists since I've been working with FPGAs, but it has been more buggy. So it's basically a tool which is a visual tool which you have blocks and you load the blocks in this case being IP cores. And you can also load in your custom, but then you need to export it as IP core, as your own design, and then you load it in. And that's where where really this IP core naming really gets fuzzy. And then you can have multiple various blocks, modules or IP cores in this case, exactly written. Then you can basically make them interact with each other, and then they perform overall functionality of the FPGA design. Very useful, especially for quick design flows when you have IP cores, or you say, I have this and this design, I want to use this. Yesterday I just tried for the fun of it, make a RISC-V processor on the RTX with some Ethernet. Click, I will show that, and then it's done. I'm not sure if I will make an assignment out of it. That's why I will show it now in a lecture, but just to give you an idea. It basically visualizes, it's abstract on low-level detail. So you have a lot of very high-level structure, and it makes it very simple to understand. On the other hand, if something doesn't work, good luck understanding it when you try to avoid a VHDL or FPGA design, because the errors will still be FPGA related, right? So, like, oh yeah, I'm working with a high-level tool, but I have no idea what all these warnings and messages mean. Of course, it's unavoidable. So basically, it tries to simplify the development process by just having simple blocks. You throw them together, you connect them, and this is often used for IP core-based designs. As said, you can use only IP cores made to make a full design if you have the right IP cores, the right toolage. If you've been a bigger company which has a lot of IP cores, you will not. There will be teams which do overall designs, and there will be teams who do low-level optimizations or new developments. And the high-level team will never write any HDL, except for they really need to debug something or dive into that. So that's just because the designs have gotten so big, these things become actually very useful. Good. I hope at least answered out those questions. This will be very useful for any kind of assignments. One thing actually which I forgot, IP cores, I don't know, might have been written here. Oh yeah, here. I did not say it, but it's written on here. Many IP cores come with like simulations. So you actually have the IP core plus a simulation to test it out. but they might be constrained in what the simulation does, and it does not anymore work in the context you try to use it with. But at least gives you a reference what you want to use.
You can put it in your own simulation later.
Yes, for example, you can, especially for IP cores, like for memory blocks and so on, these test benches will allow to emulate the memory. Because right, you have your IP core which interfaces with the physical memory, but if you want to simulate that, you would have to write that memory. And often when people integrate a memory into their design or provide an IP core for that, if I have a Samsung memory, some vendor might be, oh, this is a radiation-hardened memory. I will provide a solution to integrate this radiation-hardened memory into an FPGA. Then they will do this, but they also will emulate the memory, because otherwise you will never be able to simulate any kind of image or whatever you load in and out of the memory. And that's very, very, very common. Otherwise, it's going to be like, thanks for the memory, but I have no idea if it works, how it works, what it does. That I would have definitely there it is required. When it goes to higher functionalities like algorithms and so on, the quality of those might decrease depending on, of course, which your vendor is, who your partner is, and those kind of things.
Quality of the simulations.
Yes, because it might just do for the niche scenario, and of course these developments are expensive, so it costs a lot of time to do the simulation correctly, and also to verify then that is actually the risk is when you give a simulation that it may not represent the actual behavior or something which is relevant, especially for a memory block. You would have to exactly prove that your simulation is as the memory block. So in the more complex the block which you try to simulate is, the more time you will spend on it. So it's quite a complex task to do. So you might want to make a simplification, but then it does not fully resemble anymore and all these kind of things. So it's a trade-off which you have to do in simulations. Yes, I think I'm gonna try to connect the screen here. I'm gonna just pull up my OBS. Where's the cable now? Oh, you have it connected.
So you want to share the code?
Yeah, I have like two short examples. Could also be in this seminar, but it's easier now here, I think, when this works.
How do you record?
I can do the OBS and upload it. And I can connect this here as well. No, I can't. Can I? No, I can't. How did you connect it in the end? No, I didn't.
No, this is not connected. This is just onboard recording.
Oh. Yeah, then it's fine now. Then I just make a... I need to open. I hit. Vivado has this annoying bug that when you change screens that it does not allow the scaling anymore. So, and in the meantime, you can give me the HDMI though.
Yes.
And I can load up OBS as well again. It's not still open. No.
Just record your full screen then in OBS.
Yeah. I just have to. I don't even have to do the audio line, really, do I?
Yeah.
I will do
audio from here.
Good.
Once the recording.
Okay. Yeah, then we just have to overlay.
Just merge them afterwards.
Yeah. Display capture. There we go. And it's duplicated.
It's duplicated. Okay. Delete the video capture, or at least resize the display. Yeah. Delete.
Yeah.
And make the display full size.
Something. No.
That's it. Yeah, that should work.
This. Then I can just start recording, I suppose.
Not streaming.
Oh, yes.
Not streaming.
So this should work, and then I can just go here and quickly into this design. That's your assignment essentially. We'll not do any synthesis or anything, just like to show you the blocks again in the code. Thought about putting it into the slides, but that was a bit messy, sorry. this should be a bit easier. Yeah, when you're in battery mode, it takes a little bit longer. This up is roughly visible. So, just to show you how this is also going to look in code, we have here, I can minimize this. So here, first of all, on the top of the code, you load the libraries. So you use your library, and then you use these packages. So now I think after this, hopefully you will understand the different code blocks. We will not go into much more code level detail, but I thought it would be very useful for you to understand the different parts which you have. And then you have here an entity. You have an entity which is a generic and a port. And I mean, you had already the assignment on it. I guess you kind of managed to work with it. But as we go bigger and bigger, I wanted to make sure that this foundation is also understood. And now you have hopefully seen it as well, used it yourself, and now I will give full, hopefully in any gap. We'll talk about this in detail also in the assignment again. Here you have then a component, which is basically the URTX, which is your other entity, which will define all the ports in the generic. The URX, the signals are here in between, that's less relevant. And then here, exactly, you have here already started the architecture. That's just how the syntax is. I'm not going to go into that now. And then you have here your instantiation and your connection. So you basically connect here via port and import map and generic map, everything to each other. And this is essentially when I would remove this here, just for demonstration purposes. Let's see, should hopefully work. When I do this, this one will disappear. Yes. It will still have this one here because I've loaded that file into the project, but it will just disappear. So this part here, the map, is actually what connects my design to each other. And that's where when we would go back to the slides now, where I can, when I make another one of those, and I can call it URL1, whatever, right? Oops, not A. It should ideally have two of them. So this is how I can very easily scale up the entire design to multiple ports. Of course, I need to now make sure that my signals and those things are correctly connected. I've not done this now, but it's just from a design hierarchy point of view to make that well understood.
Can you reuse the ports?
The ports, yes. The signals, you have to understand that signals are going to be the same. So you can actually split the signal over multiple entities, but it will also have the same signal.
Yeah, but sometimes you want it.
Exactly. So that's just something to be kept in mind. I actually like to write then usually a logic a bit further down, which like an arithmetic logic here, which basically will lay out this a bit more, because if you do this in the port map, you might lose the overview. So writing it separately as with a few lines separately, like here, something like that you want to have, what you have assigned to which here, something like that you want to have. Let's say I would now need to make multiple. I will just give an example. So TX load, right? Equals. Am I writing the right stuff? I am. Equals, I don't know, from the other one, yeah, here. So this is a classic example. Sorry, let's do it this way. You have the data. You have here the data signal created. This will go the data from Rx, from the receive part, to the TX part. And I would now make it multiple times. I would send everywhere the same data, but I want to have a data 1 and data 2. So I might want to combine it or split it up into multiple signals at a later point. It's something which I actually might do in the assignment. That's a good idea. But before I write this up now and confused, I'm going to leave this out for now. And then, of course, then we come to the last. So we're in the architecture, in the component. We have instantiated our components. Then we will have here the transmit, the process, where we will go through. Procedures and functions I will probably do in the assignments as well. But here you have understood at least the design hierarchy, how these kind of things build up. And of course, I could now go in here, and technically I could potentially make even another UART simple within here. So I can really blow this up as into how many layers, whatever I want on multiple layers. So that's very modular design. If you think about this beforehand, it will be quite nice. That's the one thing which I wanted to show. And actually, I do not have to open a new project because I do not have here, it's just as an example. I can create a block design. And I will see how much we will use this. I just want that you have seen this as part of, to visualize what we just discussed with the block design and the IP cores. There's two parts. I will have an IP catalog, and the IP catalog will have a lot of different things. Can I make this smaller? Yeah, here's the IP catalog. So I have all kinds of interfaces. I have math functions to video, whatever, AXI, here bitmap, scalable, 2D graphics accelerator, whatever I want, right? So there's a lot of accelerators around. Video encoding, video mixer, video connectivity. So it's actually, let's see. I can give a DisplayPort IP core immediately and can just load it in here. For the fun, because I've tried it out, I will stick to what I tried out beforehand. I can just add here an IP core, and I can search for a processor. And I can now load an ARM processor or whatever. Micro, there we are. So I could load an ARM processor, which is external, or I use the Microplace internal one. We'll use the new one, the RISC-V one, otherwise I have to go through process. Then you can do here block automation, and it will ask me a lot of questions. I will just click here OK for now, for the simplicity of it. You saw the configuration. I can configure a lot of things here. And then there will appear a lot of other blocks. Let's see. No, I can't even do anything in between. And then it will create me a local memory access. It will create me a clock wizard. It will create me resetting of the systems. It will create me, depending what I selected, a watchdog, for example, as well. And then I basically have the entire processor implement on my FPGA. Do not know how it's going to work. I have not tried those, especially this one I have not tried. It just was recently released. And then you have all these kind of things. You have a processor reset, as I said. You have debug module and a clocking wizard. So that will define the clock and adapt the clock. What I can do now, even, and this works only to limited functionalities. I have here again different Ethernets. I don't want to have a 10G Ethernet, right? I think I will just go for the light version because I just need some Ethernet connectivity, not with specific bandwidth. And then this block appears here. And then what I can do is, hopefully, I can make here's all the different interfaces, and I want to, in this case, just as a demonstration, does not mean it's correct. I can select everything what is connected to each other, and I can let it connect everything to each other. And if I go through it, it kind of at least makes sense. So I will have, because we have not have the interfaces, but essentially I have a master, which will go to my Ethernet, have a reset, but also, here. I will get the data from a slave. The Ethernet is obviously a slave in this case. Get the data out into my Ethernet, and I will also get in the other direction the data back in here into my Ethernet ports on my hardware layer, into my pins. And this way I have written just right now a RISC-V processor with Ethernet. And of course there might be bugs in there, but because I've just clicked it through. But if you know what buttons you would select here and what you do, then this is not more complex than this. And this I find kind of surprising what you can do.
Could be bugs.
I can do incompatible settings.
Okay.
So I can select, I can select the wrong bus width. It would warn me about this, but sometimes it just doesn't quite work, or it doesn't automatically recognize the connections. I run now auto connection. There's of course, if I have especially if I have multiple slaves and masters, it will just connect them differently. I need to be very careful that I, in the outer connection. Wait, what was it here? In the outer connection here, that I select that I connect the right things to each other, right? I cannot even select here things right now. So I need to make sure. Sometimes I want to manually connect them, or sometimes I do not want to have the reset connected, right? Then I would not select this in here. But in this case, I said I want to have everything, and then I will do it as well. But I'm saying this because I've had instances where this kind of stuff unfortunately did not work automatically correct, and then you stand there and you do not understand. Again, you still have to understand the hardware layer. Good, but actually that is it from us. I just want to have that included in the lecture to give you the physical representation what we talked about. I think the seminar would have been too far away. Yes. And this, of course, exists also not only in Vivado, it exists in Quartus and Libre to some extent as well.
You just said when you do auto connect,
yes,
sometimes it doesn't work and you don't understand it.
Because in the beginning I didn't know how to connect it.
I mean, generally.
Yes.
What is the right approach to fix this problem?
In general, I would think about how I want to connect it, and I would do the manual connection myself to figure these kind of things out.
All of them?
Yeah, I mean, it's not that many, of course, you can also open up the port and make it a lot more, but it's a bus interface. We will come to the interconnects and those kind of things. But modern tools understand what is a bus, and you can even write it as a bus in VHDL. And then this tool will recognize as a bus, and that will connect all of the ports to somewhere else. And that makes it kind of nice. That's why you can automatize it as well. But there might be something which are wrong, and you have to really, let's put it this way, if I run AutoConnect without thinking about it, I will obviously not know what is incorrect. So I need to either connect it myself or really go through the connections and see what is going wrong. And I personally, for example, I would just remove all the connections and think it through. Because otherwise, I just, this is logical, and because you have this bias of how it was. If you look at debugging code, sometimes it helps to look from scratch. Yeah, good. I think I will stop.